So we've just had a look at how we can use half equations to show if something's being reduced or oxidised, and therefore is it the oxidant or the reductant. Another way we can do this, which actually is a little bit quicker, especially if you're given a full equation and don't know how to break it apart into half equations, another quick way, or quickish way, is to use oxidation numbers. We've just read about the rules that we're going to use to allocate oxidation numbers to atoms, or what we sometimes call oxidation states. We're going to go through a few ideas here to see if we understand those rules. So the first thing we look at are our elements. So our metals, such as magnesium, our non-metals, such as oxygen, or carbon, or anything like that. What oxidation state does magnesium metal have, according to our rules?
0.
0. Okay, so the magnesium in magnesium is 0. What about the oxygen in O2?
0.
0. Okay, what about the oxygen in ozone?
0.
Cool. So this one's our easiest rule. Any element, even if it's an allotrope, so a different structure of the same element, every element has an oxidation number of 0. Okay, so if you've got an element, so where it's just one type of atom, doesn't matter if there's numbers next to them or not, but if it's one type of atom, the oxidation number is always 0. However, a lot of these things can become monatomic ions. In other words, they can become ions made up of simply one atom. I've chosen magnesium and oxygen for a really good reason, because we know about the combustion of magnesium in air, which it's reacting with the oxygen there, to become magnesium oxide. Magnesium oxide has got magnesium ions and oxide ions in it. Could we have a guess or work out what our oxidation number of magnesium is now? And 2 plus. Cool. We actually say +2, but 2 plus would be okay. Okay, using that, what would we infer oxide would be?
-2.
Cool. -2. So our rule here is just as easy. Whatever the charge of that ion is, becomes its oxidation number. That's pretty cool. So, if I know what ion it becomes, I know its oxidation state.
How do you figure out whether it's a monatomic ion or a polyatomic?
Oh, right, okay, so monatomic means made up of only one type of atom. So polyatomic would be something like sulfate, where it's got sulfur and oxygen and an overall charge. I will write that because we're going to do that one shortly. We're going to do SO4 2 minus, we're going to look at sulfur, and SO3 2 minus as our last thing. Okay? So I will answer that later, but how do we know it's only made up of one type of atom? Again, so a bit like our elements, so sort of putting them in lines to make that a bit helpful. The quickest way to know the answer to this is to use our periodic table. Where we should know our columns or our groups link up to, we have +1 ions, then +2, then +3, none, -3s, -2s, -1s, and then the noble gases. So knowing that the groups line up to different charged monatomic ions is worthwhile for this. Really good to know. So if I heard you say, oh, what's chlorine and chloride? I'd say, well, where is chlorine? Oh, it's in the second last group. So therefore it makes -1 ions. So chloride, the ion chloride must be Cl negative, so it has a -1 oxidation number. Be careful, chlorine can have multiple oxidation numbers depending on what it's bound with, but the chloride ion, sodium chloride, magnesium chloride, hydrochloric acid, is always -1. Right, the reason I used oxygen will take me to my next little rule, where if I've got something that contains oxygen, I can actually work it out. So I'm going to go for CO2, so not something ionic, because if it was ionic I could just use that rule, it'd be a bit easy. So I'm going to use CO2 and SO3 as my examples. I want to find the oxidation number of the underlying atoms using my oxidation number rules. The rule I'm going to use is, actually, whenever oxygen's with something, I'm going to pretend it's an ion. It's not, but I'm going to pretend it's an ion. And the reason I can do that is because it will have contributed or had 2 electrons involved in bonding. So it's got an oxidation number of -2. So knowing that this has an oxidation number of -2, and there's 2 of them, I can work this out using a bit of horrible algebra. So if I have my carbon, and I've got 2 oxygens, and I'm going to pretend that oxygen is oxide. It's not really, though dioxide, I suppose you could argue it is. What's the charge, as it were, so oxidation number of oxide? -2. And this is a molecule, so they have to add up to 0. Just like the elements have to add up to 0 because they've got no charge. Same thing with molecules. All of their oxidation numbers have to add up to 0. So therefore, if I work this out, carbon is going to equal +4. Because 4 minus 2 minus 2 equals 0. Therefore, it's a molecule with no net charge. That's pretty cool. So we're pretending that oxygen is -2. Right. Therefore, can we work out what the sulfur is going to be in sulfur trioxide? So sulfur plus 3 times what value?
-2.
Awesome. Equals what value?
0.
0 because it's got no charge here. Cool, it's a molecule. Therefore, sulfur equals +6. Sulfur's another really funky one. It's got multiple oxidation numbers. You have to work out what it's bound to. You'll see that when we get to polyatomic ions. Okay? I want to pause there. Any questions on that? 'Cause I'm about to throw you the first exception to the rule. No questions? Cool. Right. The problem is when we come across this particular chemical, H2O2, which is one we met in our half equations work. H2O2 is a bit of a pain. The reason it's a bit of a pain is that the hydrogens we know have got a +1 oxidation state. Therefore, to stick with our rule that they have to add up to 0, what would the oxygens have to be in this case?
-1.
-1. So this is our exception to the rule. The oxygens in this are -1 instead of -2. It is the only time they're not -2. Or, of course, 0 if they're the element. It's the only time. So it's an exception you have to know off by heart. Alright? There are other peroxides, and that's also -1, but this is the only one you will meet this year, so it's the only one I want to throw at you. Okay? So it's called a peroxide. Okay, and that per is the important bit. It tells us that it's -1 instead of -2 for the oxygen. Okay? So, having that leads me quite nicely to things containing hydrogen. This must be a pretty important rule with no exceptions, hopefully. Things containing hydrogen. What did I say the hydrogen had to equal there?
+1.
+1. So therefore, if I gave you this CH4, using all the rules we've learnt so far, doing it as a bit of algebra, we want to find the carbon. So I'll do it a bit like algebra. C is my unknown, and there are 4 lots of what number?
+1.
+1. Has to equal what number because it's a molecule?
0.
0. So what +4 equals 0?
-4.
Now do you notice that up there carbon was +4 and down here it's -4?
Yeah.
Okay, so be careful. Just because you get, carbon's +4, must be +4 in this one as well. No. A lot of things have got variable oxidation numbers. They can be pluses or they can be minuses. They can be different numbers, which you can see as sulfur shortly. That sort of thing.
What stops the hydrogen from becoming a hydride?
About to get to hydrides, because
Okay.
that's our exception. Okay, good one. So, if hydrogen is bound to a non-metal, carbon, nitrogen, oxygen, so water, hydrochloric acid, then it will be +1. If it's bound to a metal, we call it a hydride. So, for example, LiH, lithium hydride, it's used for batteries. Okay, used for long-lasting batteries or cells. In this case, the fact that lithium is +1, because it's an ion, so it has to be +1 according to our rule up there. Rule over there. It's a monatomic ion, means our hydrogen must be -1. Okay. The easy rule is it's bound to a metal. If it's bound to a metal, hydrogen is a hydride, and so it's the negative ion. So this rule here comes in. It's a monatomic negative ion. Yep.
Because that is that the lithium hydride? Is
Yes.
that bond like really strong? And then when it's like reacted, because in batteries, it's like exothermic, so it's releasing a lot of energy.
It is a strong bond because it's ionic, whereas most things that hydrogen bonds with is covalent, and that's when it's the +1 oxidation state, is the covalent bond. So yeah, it is. It's a much stronger one. Yeah.
So there's two ways of figuring out these equations, like with that chart with the reduced and oxidized forms in this.
Yeah.
So is there two ways you can figure it out?
Yes, I'm going to show you that with one example that I'm going to write down here in a moment. Okay? Right, the last thing we have to know is our polyatomic ions. So let's say I had Na2SO4. The sodium's a spectator ion. Sodium very rarely is involved in oxidation reduction. Knowing that sodium's in group 1, it's a +1 ion, I then can work out that sulfate, SO4, must be 2-. So I can write out the equation for that. Sorry, I don't use this colour. So this could be, say, from Na2SO4, this could be Na2SO3. They're both chemicals you might meet in this unit. So knowing that sodium's a +1 ion, I can work out that if there's two of them, this is a 2- ion. Same thing here, it's a 2- ion. So I need to work out their oxidation numbers. And they're going to be different, even though they're pretty similar chemicals. This is really similar to working it out for this. The difference is, see how they equaled 0 because they were molecules? These are not molecules, they're ions. So S plus 4 times -2, because it's got oxygen in it, is not going to equal 0, but it's going to equal the charge of the ion. Therefore, in this case, sulfur, again, is equal to +6, like we saw in sulfur trioxide. Because 6 minus 8 equals -2. Okay, this also exists, sulfur trioxide. Sorry, start again, sulfite, which is like this one, sulfur trioxide, but it has a charge. It's not a molecule, it's an ion. So in this case, sulfur plus not 4 times -2, but 3 times -2. Cool. It's going to equal, again, the charge -2. So if I solve for that, in this case, sulfur is +4. Okay. So here we've got all of the rules we've just read applied to some different species. So we call these things that are involved in redox species. Now I'm going to go back to one that we looked at in our balancing equations video, where permanganate turned into manganese 2+. We know it's reduction if we complete the half equation. But actually, I'm not going to do it. I'm not going to complete the half equation at all. I'm going to apply these rules to try to work it out. Is one of those oxidation numbers really easy to work out without even thinking? Which one? Cool, because it's going to be, had some zeros, some 2+. What do we know for? 2+, cool, 'cause it's got the, okay? So it's got a +2 oxidation number or oxidation state. This one here is going to be manganese -8 equals -1. So what oxidation number would it be for this? plus 7. Awesome. What's happening to that number?
Reduced by 5.
It's being reduced, did you say?
Yeah.
And this is one of the reasons we call that process reduction. The oxidation state or oxidation number is being reduced. If it had gone up, it would be oxidation. A little bit quicker than doing a half equation, isn't it? Which is why we often use it as our first way to check if something is oxidation reduction or not. And if it's not, we just say there's no change in oxidation number for any of the atoms, not redox, and we move on to the next question. Okay? Because in this unit we're only worrying about redox reactions. So if they're not redox, move on. Any questions on that?